Here we are at your final video lecture of the semester. In this chapter, we're going to discuss specific types of solutions, namely acids and bases. There are lots of different ways that we can define an acid or a base. Here are two of them on this slide. These are perhaps the two most common ways that we express what an acid is versus what a base is. According to one definition, one that we might already be familiar with from previous work in this course, the Arrhenius definition, an acid has an H+ cation in its chemical formula. To act like an acid, a chemical compound needs to be dissociated or split apart into its ions in water to free up that H+ cation. Examples of acids, therefore, are anything that has an H+ and is dissolved in water, HCl or H3PO4. By definition, a base has hydroxide ion in its chemical formula. Again, in order to act like a base, a chemical compound with a hydroxide anion must be mixed with water so that that ionic compound can dissociate to free up OH- ions. Examples of bases therefore include sodium hydroxide or barium hydroxide. But this Arrhenius definition alone is not sufficient to encompass all of the things that affect the pH of a solution. Acids and bases manifest in form of a measurable quantity called the pH, which we'll define later. But things that aren't NaOH and BaOH2, for instance, can still influence the pH when mixed with water. And so we need a bit broader definition in order to account for those substances. Hence, a second way to define acids and bases, called the Bronsted-Lowry definition. Under this definition, an acid donates a proton, an H+ cation. In so doing, we can call an acid anything that falls under the same definition of Arrhenius, because all a Bronsted-Lowry acid requires is an H+ cation in its chemical formula that can be freed up by mixing with water. So this effectively gives us the same definition for an acid as we had above. And anything we'd previously defined as an acid can still be defined as such. The real place where the Bronsted-Lowry definition shines is in our ability to expand our definition of a base. According to this theory, bases accept protons. So no longer does a base have to have hydroxide ion in its chemical formula. Under the Bronsted-Lowry definition, a base simply needs to be able to accept a proton, an H+ cation. In order to do so, our base must have a lone pair of electrons somewhere on a highly electronegative atom. For instance, in ammonia, NH3, we've got a lone pair of electrons on the central nitrogen. That lone pair of electrons is attractive to an H+ cation. In carbonate, CO3 2-, we've got lone pairs of electrons on peripheral oxygen atoms. These lone pairs of electrons are again attractive to H+ cations. And then lastly, in hydroxide, our oxygen atom has lone pairs of electrons that are attractive to H+ cations. Each one of these things, by virtue of having lone pairs of electrons on highly electronegative atoms, is capable of attracting H+ cations, and so can act like a base. As we mentioned earlier in the semester, the real picture that we think about for acids and bases are free protons that don't actually stay free protons for very long. They like to piggyback on water molecules because free protons, H+ cations, are highly unstable things that seek out any source of electron density they can. The real picture for what an acid is is the hydronium cation, H3O+, rather than a free standalone H+ cation. But that's a little bit beyond the scope of what we really need in this course. So I thought I would offer it so that you have seen this, but we're not going to belabor this point for too long. Instead, we'll talk about examples of some acids and bases. The Arrhenius theory for acids and bases tells us that acids have H+ in their formula, while bases have hydroxide ion, OH- in their formula. When substances that have H+ in their formula, acids, or have hydroxide ion in their formula, bases, are mixed with water and fully dissociate, we say that those things are strong acids or bases. You should know 7 strong acids. These 7 strong acids are HCl, HBr, and HI, hydrochloric, hydrobromic, and hydroiodic acid, HNO3, H2SO4, HClO3, and HClO4, nitric, sulfuric, chloric, and perchloric acids. These 7 acids are the 7 sole strong acids. These strong acids fully dissociate when mixed with water. For example, if we mix hydrochloric acid, HCl, with water, if we place hydrochloric acid in aqueous solution, we expect that it dissociates or breaks up into its cation, H+, and its anion, Cl-, fully, so that there is no more intact HCl molecule, and instead, this substance exists as H+ cations and chloride Cl- anions. Similarly, a strong base is anything that's soluble and contains hydroxide ion. Strong bases are hydroxide ion containing ionic compounds, which are soluble in water. We can identify compounds that are soluble in water based on our solubility rules. An example of a compound that's soluble in water and contains a hydroxide anion is sodium hydroxide, NaOH. When we mix NaOH with water, it fully dissociates, like the hydrochloric acid we saw in our previous example. It breaks apart into sodium cations and hydroxide anions. And according to our Arrhenius theory of acids and bases, the presence of hydroxide ion in aqueous solution renders this substance a base. Strong acids fully dissociate, strong bases fully dissociate. A strong acid includes any of the 7 in this list. A strong base includes anything that has a hydroxide ion in its ionic chemical formula and is soluble in water. There are many examples, however, of acids and bases that don't fully dissociate, that weren't part of the list on the previous slide. All of the things that weren't on the list on the previous slide we consider weak acids or weak bases. According to the Bronsted-Lowry theory of acid and base chemistry, a weak acid is something that gives up partially its H+ cations. A weak acid does not fully dissociate. Instead, a weak acid will only give up a few H+ cations per mole of molecules mixed with water. An example of a weak acid is acetic acid. Acetic acid, or vinegar, has the chemical formula HC2H3O2. When mixed with water, 1 mole of acetic acid molecules might only give up a handful of H+ cations in dissociation. In other words, the vast majority of acetic acid molecules remain intact as this substance seen here. We can describe or illustrate through a chemical reaction how this lack of dissociation or full dissociation differs from the complete dissociation we saw on the previous slide for strong acids by using not just a single arrow that points in one direction, but two arrows that point in opposite directions to indicate that we reach a balance between our acetic acid and dissociated ions, H plus and acetate. This double arrow is an equilibrium arrow that shows that this reaction doesn't go to completion. In other words, not all of the reactant acetic acid will dissociate into H plus and acetate. Instead, a balance is reached between the stuff on the left-hand side and the stuff on the right-hand side, and we have all three of the components by the time our reaction reaches a balance or equilibrium. In a similar vein, weak bases do not fully dissociate either, but still somehow indirectly produce hydroxide ion in solution. A weak base does so by reacting with water molecules themselves. An example of a weak base, ammonia, NH3, can react in water to form hydroxide ions. When ammonia reacts with water, it can steal a proton from a water molecule. This process likewise reaches an equilibrium. It doesn't go to completion, meaning that not every single ammonia molecule that's mixed with water will steal a proton from a water molecule. Instead, a balance is reached, and this reaction achieves an equilibrium. When ammonia steals a proton from water, it gets an extra H and an extra charge. And what's left from water after it's lost a proton or an H plus cation is a single O, a single H, and one less charge. This is the source of the hydroxide ion. A stolen proton from a water molecule generates hydroxide and makes this solution seem like a base. Again, a weak base, like a weak acid, doesn't react to completion, and instead a balance or equilibrium is achieved. And the extent of the reactions that we saw on the two previous slides dictates the pH level in solution. The stronger the acid, the more likely it is to have a low pH. And the stronger a base, the more likely it is to have a high pH in solution. Overall, pH values are centered at 7. We say that at 25 degrees Celsius, pure water has a pH of precisely 7. pH is below 7 suggests that we are dealing with acids. And the stronger the acid, again, the lower the pH it can generate. Acetic acid is a weak acid, vinegar. And vinegar in store-bought solution has a pH somewhere around 3 or 4. Stomach acid is hydrochloric acid. And in your stomach, that hydrochloric acid has a pH around 1. We can identify pH in solution either through direct measurement or through the use of some sort of color-changing indicator. An indicator, like litmus paper, turns red in the presence of an acid. At pHs above 7, we're dealing with bases. The stronger the base, the higher the pH. Ammonia, like we saw on the previous slide, is a fairly weak base. In solution, it might generate a pH around 10 or 11. Whereas drain cleaner, lye or sodium hydroxide, can generate a pH around 14 in solution. We can directly measure pH through a digital instrument, again, or we can use a color changing indicator. In the presence of bases, litmus paper and universal indicators turn blue. So, if we were to make a direct measurement on pH using a digital device, it would be convenient for us to know where these numbers come from in the first place. In other words, are these just arbitrary numbers, or is there some method to the madness of this 0 through 14 scale? Well, the answer is that there is a mathematical way to describe pH. That letter P in front of H really stands for covert mathematical operator. We can think of that P as meaning take the negative logarithm of a quantity. Therefore, placing P in front of H means take the negative log base 10 of the concentration of H plus cations in solution. If we put P in front of OH, that would mean take the negative log base 10 of the concentration of hydroxide ions in solution. What this means for us is that pH is a direct measure of the H plus cation concentration in solution. For acids, like we saw on the pH scale on the previous slide, a low pH corresponds to a large amount of H plus cations in solution. Why is this? Well, if the H plus concentration is very large, then the log of that large number is itself big. Put a negative sign in front of a big number, and we've got a number very close to or less than 0. Certainly less than 7. So, what we say is that as the H plus concentration gets high, our pH gets low. At the opposite extreme of this pH scale, where we're dealing with bases, hydrogen ion concentration is extremely low. Instead, it seems more reasonable to think about not hydrogen ion concentration to predict what's in a base, but rather hydroxide ion. If hydroxide ion concentration is what's high for a base and hydrogen ion concentration is low for a base, we should probably think about OH down here. At this extreme, the concentration of hydroxide ion is large. And it can be more convenient to think about taking the negative log of the concentration of hydroxide ions when we deal with bases. But that would preclude us, it would seem, from being able to say something about a pH value. But it turns out that we can perform some mathematical operations that show us the relationship between pH and pOH. And this is a quantity and relationship that you should be responsible for knowing. That for a given solution, the pH plus the pOH for that solution equals 14. In other words, the negative log of the concentration of H plus cations in that solution plus the negative log of the concentration of hydroxide ions in the same solution equals 14. For example, in dealing with these logarithms, we can think about a solution of an acid like formic acid, which has a pH of 1.88. We can calculate the pOH of this formic acid solution, and we can calculate the concentration of H plus cations. In addition, we'll also calculate the concentration of OH minus ions, all in this solution. We're going to use the tools that we developed on the previous slide. Namely, that pH is equal to the negative log base 10 of the concentration of H plus cations. pOH is equal to negative log base 10 of the concentration of hydroxide ions. And together, pH plus pOH equals 14. So, for one thing, let's calculate the pOH of this formic acid solution. To accomplish this, let's take advantage of this third equation. pH plus pOH equals 14. We know the pH of this solution is 1.88. Added to the pOH of this same solution, we get 14. So take away 1.88 from both sides, and we find that the pOH must be 12.12. As an aside, let's calculate the concentration of hydroxide ions in this solution of formic acid. Now that we know the pOH, can we determine the concentration of hydroxide ions? For this purpose, let's take advantage of the second equation, that pOH is equal to the negative log base 10 of the concentration of hydroxide ions. In other words, 12.12 is equal to the negative log base 10 of hydroxide ion concentration. And we'd like to determine this concentration, meaning we have to undo a logarithm. The first step in undoing this log is to move the negative sign over to the opposite side to get a log all by itself. We'll get rid of that negative sign, move it over. The next thing that we have to do to undo a logarithm is to raise 10 to the power of both sides. A logarithm just simplifies the way in which we count. It gives us powers of 10 relationship. So to undo a log, we raise 10 to the power of both sides. Raising 10 to a log gets rid of that log and leaves us with just the quantity that we'd been taking the log of in the first place. Here, hydroxide ions. We say that the concentration of hydroxide ions is equal to 10 to the negative 12.12 power. And if we punch that into a calculator, we'll get a really small number, namely 7.59 times 10 to the minus 13 power. This is the molar concentration of hydroxide ions in this formic acid solution. We can take a similar approach to determine the concentration of H plus cations in this solution. The equilibrium concentration of H plus cations, or the concentration of H plus when our formic acid has balanced out in its mixing with water. For this purpose, we'll take advantage of the first equation, and we'll do a similar approach that we took in part B. We know the pH of our solution of formic acid is 1.88, and we know that that pH is equal to the negative logarithm of the concentration of H plus in that solution. In order to undo this logarithm, we have to move a negative sign over. And to complete this problem, raise 10 to the power of both sides. That gets rid of our log on the right-hand side, and all we'll have to do is punch in our calculator 10 to the negative 1.88 power. That gives us 0.013 molar. Our concentration of H plus cations in this solution of formic acid, 0.013 molar, is orders of magnitude larger than the hydroxide ion concentration in this same solution. Because there's vastly more H plus in this formic acid than there is OH minus, formic acid acts acidic. It has a pH less than 7. So to round this discussion out, let's do a little bit more practice calculating pHs and determining concentrations of H plus in solutions. So we have 4 practice problems to work on here. We're going to calculate the pH of an acid and a base solution. And then we're going to determine H plus concentrations in solutions with given pHs. So for one thing, to calculate the pH of a solution, we need to take advantage of the equations that we wrote on the previous slide. If we know the concentration of H plus cations in a solution, we can determine pH directly by taking the negative log of their concentrations. If, however, we know something about hydroxide ion concentrations, we can determine a pOH directly by taking the negative log of OH minus concentration. Together, if we know a pH or a pOH, we can calculate the other, knowing that pH plus pOH for a solution equals 14. In a solution that's 0.25 molar hydrochloric acid, this acid, which we can recognize by its chemical formula, it has H plus in its formula. This acid fully dissociates. This is an acid, and what's more is it's a strong acid. We just don't have time in this course to talk about the distinction between calculations for strong and weak acids, so we'll suffice it to say that so long as we can identify an acid, we can calculate the pH for that acid directly from the concentration of H plus cations. We know that pH is governed by H plus concentration, and if HCl is a strong acid and fully dissociates, then the concentration of H plus that it generates must be equal to the formal concentration or starting concentration of hydrochloric acid we had in solution, 0.25 molar. The pH is the negative log base 10 of that concentration, 0.25. If we punch this into a calculator, negative log of 0.25, we'll get 0.60. A good rule of thumb for sig figs when dealing with pH is just to keep 2 digits past the decimal point. In part B, we'd like to calculate the pH of a 0.30 molar solution of potassium hydroxide. This substance does not have an H plus cation in its formula. Instead, it's got a hydroxide anion. We can recognize this, therefore, as a base. And technically, this is a strong base because it's fully soluble in water and produces hydroxide ions through direct dissociation. There are no H plus cations given up directly from this chemical formula. The best that we can say is that we know a concentration of hydroxide ions instead. Because potassium hydroxide completely dissociates, it's fully soluble, the concentration of hydroxide ions that it produces must be equal to the formal concentration of KOH that we put in solution, 0.3 molar. And from here, the best that we can do is determine a pOH value. When we're dealing with bases, the best that we can do is calculate a pOH directly. That pOH is the negative log of the concentration of hydroxide ions, 0.30 in this case. The negative log of 0.30 is 0.52. This is not yet our pH though. To determine our pH, we can subtract from 14 our pOH value we've just calculated. The pH of this solution is 14 minus 0.52, which is 13.48. a pH that seems much more reasonably appropriate for a base like potassium hydroxide. So, one last bit of practice. Let's calculate what we're asked in the second portion of this slide. The concentration of H plus in solutions with given pH or pOH. In part A, we want to know the concentration of H plus cations in a solution whose pH is 2.52. For this purpose, we can directly determine H plus concentration from the first equation that we have up above. pH is equal to the negative log of H plus cations, just like we did on the previous slide. Again, we'll have 2.52, the pH being equal to the negative log of the concentration of H plus cations. To undo this logarithm, we've got to move a negative sign over to the opposite side and raise 10 to the power of either side. On the left, we get 10 to the negative 2.52 is equal to the concentration of H plus cations, or the concentration of H plus when we plug the left-hand side into our calculator works out to be 3.0 times 10 to the minus 3 molar. That's 0.003 molar. In part B of this problem, we're asked about the H plus concentration in a solution whose pOH is equal to 1.20. In this case, the best that we can do is first determine a pH from this third equation, and then use the same approach that we took in part A. If we know that the pH plus the pOH is equal to 14, then the pH in this problem must be equal to 14 minus 1.20. The pH must be 12.8. And now we can take advantage of that first equation up above. The pH, 12.80, is equal to the negative log of the concentration of H plus cations. Once more, we've got to move a negative sign over to the opposite side and raise 10 to the power of both sides, so that the H plus concentration is equal to 10 to the negative 12.8. Or, again, if we punch this into our calculator, we get 1.6 times 10 to the minus 13 molar. Now, 0.00000000000016. For this chapter, you should be able to distinguish between an acid and a base, and be able to perform calculations with log base 10, like we've done here, to either determine the pH of a solution of an acid or of a base, or given a pH or pOH, calculate the concentration of H plus cations or hydroxide anions, like we've done in these examples.